Hello. Hi, good afternoon. My name is Kylie. I'm with UfiSpace, locally here in San Jose. Hello. Hello. Good afternoon. My name is Kylie. I'm with UfiSpace, locally in San Jose. UfiSpace is a Taiwanese company headquartered in Taiwan. We have two development centers, one in the city of Taipei and one in a development center called Hsinchu, also known as the Taiwan version of the Silicon Valley. So what I'm going to talk about this afternoon is the aggregation router that used in a Converged mobile design network. And when I say Converged, I'm going to talk about a couple of things, such as how the traditional D-WAN that converts to central WAN, as well as the open WAN, how we packetize the front haul, and using an aggregation router to terminate some of those ECP connections. All right, in the next 15 minutes, I'm going to kind of go into a couple of architecture, product solutions, and then some of the customer use cases and all that. So this is our company. And first, I'd like to kind of start with a network reference architecture diagram. As some of the big carrier that are converging from the existing 4G LTE to 5G. And there's a lot of mixed environment that is being converged from the traditional one to the 5G. And sometimes you heard of the term called SA versus NSA. NSA stands for non-standard architecture versus SA is the standard architecture. These are some of the terms that you will hear. NSA meaning you have a mixed environment with the 4G LTE and the 5G versus the SA. You are converging everything into a pure 5G, a real 5G with millimeter wave and all these other things. So what we are showing here is a couple scenario. Is some of the these kind of conversion going from the traditional D-RAN, the distributed radio access network, eventually to a C-RAN, the central radio access network. And one of the key components is when you are doing this kind of conversion packetization, what you can do is you no longer have to follow the traditional semi-proprietary of one radio unit convert to a one BBU baseband unit. You kind of can support a list of cell tower with multiple RU and then go into a single pool of BBU. And it's packetizing, it's virtualizing the BBU to support multiple cell tower. And this is really what the converging as one of the benefits as we are migrating. And if you look at the 5G, this makes a lot of sense when you're in New York City, Los Angeles, you're in some of these locations where you might have a lot of cell tower in a very condensed area. Because 5G, by definition, the carrier frequency is really high. And then when a high frequency with a shorter bandwidth, if you remember your physics from college, your frequency is 1 over lambda. When the higher the carrier frequency, the shorter the lambda, so you don't travel as far. So that's why you need a lot of this proximity of the 5G infrastructure. And that also introduced the concept of the DU and the CU. So this is, I just kind of want to lay the foundation, what we are looking at and the problem we're trying to resolve. And in this converged design, we are looking at the good old CP, semi-proprietary, and then going into the eCP, which basically is packetized based on Ethernet packet. And sometimes when I'm in this conversation, people would like to refer CP, the traditional CP, as a circuit switching, and eCP as packet switching. One is kind of connection, the other one is connectionless. You know, some of the terminology sometimes we use. And then, so those are some of the things. So I just actually talk about the challenge of how we coexist and do the migration, not with the forklift. And because as we move to 5G, it requires a lot of things, what the industry calls packetization of the front haul, okay? Talk about the things that I just described, how you actually go from a traditional CCP into a regular CP, and then in between there's something called a radio over Ethernet, IEEE 1914. How do you put radio packet on top of Ethernet? So it's all these things we're trying to, coexist when you go from the distribution radio access network to the C-RAN, eventually to the O-RAN to adapt the 5G. So some of the benefit that we're trying to solve all these problems we describe is the following. When we introduce a flexible, scalable aggregation layer, what we are trying to do is we can do some of this local termination. When you have ECP connection coming out, from your front haul equipment, we are building a scalable, somewhat non-expensive devices to terminate a lot of these connections coming out, like an ECP connection, with high-density, low-cost Ethernet port in a non-blocking architecture. We try to make this thing very scalable because every time you introduce a layer in your network design, okay, like introducing a aggregation layer, really, network design 101, what you're really trying to do is to scale the aggregation of the network. You introduce another aggregation layer, and then you can scale a lot more endpoint when you go into this aggregation layer before you go directly into the core of your backbone. So these are some of the benefits that we think we can contribute by introducing the aggregation layer. So in UfiSpace, we are a white box company. We partner with Broadcom and a few other semiconductor companies. That is our upstream. Our downstream, we work with a lot of network operating system providers. A lot of them are on OCP here today. In fact, some of them are in the room here. So we're kind of looking at upstream as our supplier, like the merchant silicon, downstream as our NOS provider. And then in parallel, we work with a lot of system integrators to bring this whole disaggregated model into the market. That's kind of what we do. So in our family of the aggregation, we have a number of devices. And so far, they are all based on the latest and greatest Broadcom merchant silicon. We put 4 in the pictures today. The one that labeled in color on your left upper corner, that is our J2 box. The rest of them are using the Crumon 2C or the Q2C family. Okay, the J2 is the one that we are talking about today. J2 is one of the fastest chip that Broadcom is shipping in their DNX family. DNX usually are referring to the telco as compared to the XGS or more to the spine leaf data center. So G2 is the latest one that they are shipping in production. At UfiSpace, we are kind of like in the smaller circle within Broadcom, so they are building the next chipset. A lot of you guys may probably know directly from Broadcom, known as the J2C+. We are also building the next generation based on the next chip they are building. Is in alpha sample, but we are building another box based on that. But today, we're going to focus on things that are shipping in production. J2 basically is a 4.8 terabit per second chipset. And if you do the math, we build a 4800 gig port. And you do the math when you design those numbers, it's a non-blocking 48 port times 100 gig, equal to 4.8 terabit per second. That's exactly what the chip is designed to do. We build an aggregation box based on a non-blocking architecture using that. And then we also add some other things that we think is benefit to the telco environment, such as clocking, PTP, precision timing protocol, which I will talk about this for a second. The rest of the boxes is in the family, and they are based on something called Crumon 2C or Q2C. They are slightly below the J2 family, but we trying to have all different layers with different pricing entry point for different type of tier 2 or tier 3 carrier or different application. But we're going to focus on the most powerful box today with the J2. This is a bigger picture of what we are talking about today. The S9600-48X is the data plane is the Jericho 2 merchant silicon. And then the control plane is our Intel Broadwell 8-core 2.0 gigahertz. And then there are a couple things that we bring to the table. And the most exciting things for the telco is the clocking. This thing natively, if you look at the SMA connector on your right-hand side, this round, small miniature connector, that support direct GNSS, or known as the GPS clocking, that goes up to your GPS antenna or source in a telco space environment. In any situation, if it's a storm, a snow, or anything that you cannot lock in your satellite clock, we also support an alternative clocking solution known as the IEEE 1588 version 2 or precision timing protocol. And those are based on the transparent clock, boundary clock, powered by a grandmaster sitting at the central office going through your Ethernet connection as a precision timing protocol. And then in the industry, there's something called a Class C specification. And what Class C does is when you have a storm or weather condition, you have to switch from a GPS into a 1588 PTP clock. Class C spec basically say you have to do the switch in about 20 nanoseconds, okay, to minimize the packet drop, the jitter, and all these other delay. And then our box has been certified with Class C, doing the switching at 20 nanoseconds or less. And then we are actually trying to achieve Class D, which is the next step. But right now, we are supporting Class C, which is required by a lot of the carrier in the United States and also around the world. So, and we also do other type of clocking for reference clock and some of the legacy, the time of the day, the 1 PPS, and the 10 megahertz. So all in all, the J2 has a non-blocking design up to 48 port in 100 gig, and then with all the different clocking resources that we talk about. And here's a block diagram. I kind of color code this to make the audience a little bit easy to follow. So what we are looking at is the big chip we put in the middle with the blue color. That is the Broadcom. That is our data plane with the Jericho 2. And then underneath, you see a lot of these things that go out to the I/O. These are called the gearbox. And what the gearbox does is, we don't have a lot of time to get into the super detail. But at a high level, the gearbox actually does a very important thing for the 100 gig port. If you look at 100 gig Ethernet today, the output is using an encoding called non-return zero, or NRZ. And then the way how the J2 design on their serial is not a direct connection to fit all these 100 gig using a non-return zero. So the gearbox right next to all the I/O port is actually helping with the conversion natively from the J2 with the PAM4, make the connection into the non-return zero, and then come out to be 100 gig. We can maximize the SerDef depth at the J2 using this type of design. The control plane is the Intel. That's where the network operating system will be running. And I also want to point out another green box on your left. That is our BMC processor. BMC is the broad management controller. And these are all the housekeeping, the boot up control, making sure your fan is spinning at a certain RPM, your CPU, all the LED, all this housekeeping stuff. We do not want to design a box using a general purpose processor to do that. We want to have a separate processor. So if you look at the design, we have about 4 different processors. We have the data plane, which is the J2, and then we have the x86 CPU. That's your control plane running your network operating system. Then we have all the timing circuitry showing on your right-hand side with some FPGA programming that we do in-house to support all the clocking we talk about. And last but not the least is on your left-hand side with the BMC, the AST2600 processor to do all the housekeeping. All right, so a couple of things I want to share. These are some of the use cases I kind of mentioned a little bit at the beginning of the conversation of how we converge from a C-RAN, from a D-RAN into a C-RAN, eventually to an O-RAN. So what we are looking at is something locally terminate on the left-hand side called the front hall gateway. It translates some of the original CP conversion, and then we can make the translation into some of the other protocol or signaling like an ECP or like a radio over Ethernet. And then we can use our aggregation router on the right-hand side and do the termination before it goes into the backhaul. And then eventually we can actually take it to the next step with the Open RAN architecture as well. Last but not the least, because it's an aggregation, you don't have to use it with the front hall. You can use it in many other ways. And one of the things that we think about is whenever in network design you add another layer, you can call it a distribution layer, you can call it an aggregation layer. By adding a layer, basically you are trying to increase the scalability on your network architecture. So with that, by the same token, you can use it for other things, like your termination to some of your access devices, like an OLT or things like that that we show on the top. And these are just some of the other use cases. Because it's a disaggregated design, that's the concept from the OCP organization. We don't want to design a box that only do one thing. We want to design a box that is disaggregated enough. You use your imagination that we can have a number of use cases. For today's conversation, we list the top 3 we can think of. We talk a lot about the bottom one with the front hall, but also in the enterprise and also in the residential as well. This box, S9600, we already have contributed the specification into OCP. Our team is actually doing the design package as we speed. We expect the contribution of the spec will be at OCP later on this year, maybe early next year. And we are fully committed. All the boxes that we built, we like to share with OCP with both the specification and also the design package so that we can share with the bigger community with the telco subgroup. My contact information is up there. I'm local, and if anybody has any questions, happy to answer either now or happy to talk to you outside as well. Thank you.